Thank you. So I will do half of this lecture, and then Geoffrey will end. So I wanted to finish the analysis or some hints of how to analyze hyperbolic initial boundary value problem. This morning I ended with a proposition in the case without boundary, how to derive the standard L2 estimate. So I reproduce the proof because I will use it in the case with boundary, and so just I comment it again. If you have a Friedrich symmetrizer, so if you have a matrix X which is symmetric such that S times A is also symmetric, which David told me that I forgot to write this morning, SA has to be symmetric. Then for lambda large enough, you can control the L2 norm with an exponential bound like this. So to obtain it, you time differentiate this. This kills what you obtain when the dt hits this one. Then you have dts. Then you have dtu. dtu, you replace it by f minus a dxu. So this is for the f. And for the minus dxu, this is this. And then, so the dtu can hit here or here. Since S is symmetric, this gives you these two here. Okay? And then you use this identity that I mentioned this morning to say that this is equal to this term in f. Then you gather all the terms of order 0 and nu, so dts plus dx of SA, which is here. So this term, you can absorb it for lambda large enough by this term, as we have seen. And you have this term, and I had not commented it on this term this morning. This term is equal to 0. Okay, because it's the integral on R of a derivative. Okay, and of course, this will not be equal to 0 in the case with a boundary, so we will see this later. First, let me generalize this to higher order regularity. So let's M some real number which is positive, and assume that T0 is some real number larger than 1/2, which is d over 2 in this case. And assume that the matrix A belongs to H T0 plus 1 dot cap HM. Okay, so it's essentially, this means that it is Lipschitz. Okay. Okay, so in this case, and I let the norm of A in H T0 plus 1 cap HM smaller than some constant K. So if lambda is larger than some lambda 0, which depends on K, and also on beta 2 over alpha 0, then you have an energy estimate like this one, but in higher order norm, which is HM. So it's C of beta 0 over alpha 0. It depends on the norm of A in L infinity also, and times, so U0 in HM plus the integral from 0 to t of exponential minus lambda t prime f of t prime in HM. Okay, and so the proof of this, and under the same assumption, of course, on Friedrich symmetrizer and smooth solution. And the proof of this is very easy because you if you define, so we have seen this in the course by Elena. So it's the same. So lambda here is a fractional derivative, and let me denote V, the quantity lambda SU. Then I apply lambda S to the equation. Apply lambda S to the equation. Yes, I don't have boundary. And what you obtain is dTV plus A dx of V is equal to lambda S F minus the commutator of lambda S with A applied to dx of U. Okay, and you have V at t equal to 0 is lambda s. Okay, you don't need it. Okay, and so you apply the L2 estimate to this system and use the fact that you have a commutator estimate, which is that you can control the commutator lambda x with dx, with A, sorry, of u in L2. You can control this by a constant that depends on this quantity k that I introduce here, times u, sorry, u in h. So I put an s. Now this s is an m. I'm sorry. Okay. Okay. And then, of course, this is Grandval and this is standard. Okay. Excuse me?
It should be m minus 1.
It's dx. Thank you. It's this thing. Okay, so this is as we have seen in the talk by the course by Elena. So this is standard. Okay, and now and then you have you can have the nonlinear version of this. I will not mention this, but this is just obtained then by Picard iterates. The proof is standard. I just wanted to remind these proofs because I will adapt them, insist on what is different in the case with a boundary. So let us consider a boundary. The first question that we have is how many and which boundary condition. I mentioned a system which had P boundary condition. So let me do the analysis in a very simple case, and then you can generalize it, but see how that we can obtain conditions that determine the number and some condition on the boundary condition that you can put. So let me consider here n is equal to 2, p is equal to 1, a constant coefficient, and assume that it is diagonally, okay, disable, with eigenvalues plus minus lambda plus minus and eigenvectors E plus minus, and I assume that lambda plus minus are both positive. So there is one positive eigenvalue, one negative eigenvalue. I consider nu a vector in R2, and I look at the system and then nu dot u is equal to some g of t at x equal to 0, and so this is for x positive. Okay, I want to consider this, and I want to see if I can take any nu or not. So let us. So you could take the Laplace transform. An easy way to do it is to look like a solution. Look for u of tx of the form exponential st u hat of x. Okay, so I look a function like this, and similarly g of t. No, I don't have g of t. Okay, and so if I plug this kind of solution here, I obtain that I have s of u hat plus a dx of u hat is equal to 0. Okay, and I have that nu dot u hat is equal to g hat. Okay, and okay, and so since my matrix is diagonalizable, this is an OD in X. So OD in X, and I have a solution for this, which is u hat of S and X is some coefficients that I will write C plus S hat exponential minus S over lambda plus times the eigenvector E plus S minus S exponential plus S over lambda minus E minus. Okay? So this is a system of two ODEs. I have one boundary condition. I have another one at infinity. So I impose that I want bounded solution. So if I want bounded solution in X, this implies that C minus of S should be equal to 0. Okay, so I don't have this term. And I am sorry, I forgot the X here, of course. Okay, since L plus, lambda plus, and lambda minus are positive, this grows at infinity. Okay, and then I want to solve the boundary condition. So to solve the boundary condition, we need to take this at x equal to 0, and we need to have C plus S E plus nu dot E plus is equal to G. Okay? And I want this to be solvable for all function G of time. Okay? And so this implies that this is always solvable if and only if nu dot E plus is different from 0. Okay? And so if you want to be able to solve this kind of ODE, you cannot take any nu. There is one nu which is forbidden, which is nu proportional to the orthogonal of E plus. Okay, you cannot impose a boundary condition on this one. Okay, so this is called the Kreis-Lopatinsky condition. And this is nu dot E plus different from 0. Okay, so this is on a very simple case, but you can do the same kind of analysis and derive some conditions like this. Okay, so this is some previous analysis, but we are able to see that you cannot do whatever you want, and I could have tried to impose two boundary conditions, and I would have found that it's not possible. There's only one boundary condition that is possible here. Of course, this is related to the number and the sign of eigenvalues. Okay? Okay, first element of analysis of this initial boundary value problem. There is another thing which is very important when you look at initial boundary value problem. It's the notion of compatibility of the data. So here again, I will do it on a simple case, and you can generalize it easily. So it's 4 compatibility condition. So let me take the same example just to simplify the computation. dtu plus a dx of u is equal, say, 0, to simplify even more. Nu dot u at x equal to 0 is equal to g of t, and u at t is equal to 0 is equal to u initial of x. Okay? If I want, if u is continuous, say in 0t times R plus. R plus closed, okay? Then, in particular, what do I have? I have that nu dot u at x equal to 0 and t equal to 0 should be equal to g0. Okay, I take this at t equal to 0. On the other hand, this at t equal to 0 is u in, so this should be equal to nu in at 0. So if you want to obtain a continuous solution up to the corner, so if we want a continuous solution, u in and g must satisfy the compatibility condition which is nu dot u in 0 is equal to g0. If you don't have this condition, you cannot expect continuous solution. And then you can do this at every step. If you want u to be in C1 of 0t cross R plus, then we should have that nu of dtu at x equal to 0 should be equal to g prime of 0. And you can replace dtu by minus a dxu. So it's minus nu dot a dxu, and at x equal t equal to 0, this is dxu in. Okay, I use the equation here. So this implies another compatibility condition, which is g prime of 0 should be equal to minus nu, etc. So if you want, the idea is that in order to have a CM solution, we need m plus 1 compatibility condition. Okay, you can do by induction, then derive all this compatibility condition. Okay, so this is very important. This is something that, of course, is due to the presence of the boundary. Okay, so now that we have seen this, let us see how the a priori estimates behave with a boundary. A priori estimates with a boundary. So I can take this term here, let's call it let's call this term star here. So we do the same computations. Okay? We do the same computation as here. The difference is that now the quantity star is not equal to 0. The quantity star is equal to minus SA u scalar u evaluated at x equal to 0. Okay. And this term, I will call it B of u. So you see that this is a number, okay, and in my energy estimates is on the L2 norm of u. I cannot, so we cannot control B of u at x equal to 0 by the norm of L2. Okay, because there is no trace theorem. Okay, because the trace of function in L2 in general does not exist. Okay, and it's not in L2 in general. So no grand val possible here. Okay, but there is one situation where this can be, where you can work, is that if you have another property of two symmetrizer, which is not only a Friedrich symmetrizer, it is also what is called a Kreis symmetrizer. S is, let S be a Friedrichs symmetrizer. It is a Kreis symmetrizer if for all V in Rn we have that B of V, which means S A V dot V is bounded by here in this simple case I've taken N to be nu dot V. Nu and V, as David said, my calligraphic courses are far away, so be careful. I have V and I have nu. Okay. So why is this interesting? Because you see that in my energy estimate, so in the energy estimate, I'll put it here. So the energy estimate is, so I proceed exactly as before, and I obtain that exponential minus lambda t of u t in L2 is controlled by C beta 0 over alpha 0, the same term as in my energy estimate before. So this is the case without the boundary. I have just another term, which is for over. Okay, let me put some square. It will be easier. Okay, and integral from 0 to t of exponential minus 2 lambda t prime, and then my quantity B of u at x equal to 0 dt prime. So what would be very nice, in order to make a ground value estimate, if this quantity has a sign, if this quantity is negative, I can remove it. Okay. If this quantity is negative with, in addition, condition like this, I have some information. This gives me some information on the trace. Okay? So B of and then this is too much to ask, but actually you could ask this quantity to be negative, always negative, except in some direction, because in the direction nu dot v, you know that nu dot v, you can say that nu dot u, excuse me, is equal to the boundary condition. Okay? So you can control this quantity by replace it by the boundary condition. Okay, so then if you have a Kreis symmetrizer, no, if S is a Kreis symmetrizer, then I obtain that exponential minus lambda t, minus 2 lambda t, u of t plus the trace so I have a beta 2. Probably the constant will be wrong, but the ID, so it's alpha 2. And I should put the integral from 0 to t of exponential minus 2 lambda t prime times u, the trace of u at x equal to 0 of t prime, the absolute value, it's not a norm, dt prime is controlled by the same quantity as in the case without boundary, and I have a new term, and this term is g integral from 0 to t of exponential minus 2 lambda t prime gt prime dt prime. Okay, so this is, I will write this quantity u at x equal to 0 in L to lambda t. It's a weighted norm, exponentially weighted norm in time. Okay? And the square. And the square. And the square. And so this is G L to lambda t square. Yes?
For the Kreis symmetrizer, you want this condition at x equals 0 only, or?
Yes, you did. Yes, it's enough to have it at 0 if it's yes. Yeah. Okay, so this is nice, but of course you need to have this property. But if you have it, this is very nice because what is important we get information on the trace u at x equal to 0. I said before that I could not use the trace theorem. The trace of a function in L2 is not in L2. In this case, this tells me yes. The trace of the function in L2 is in L2. So some people, especially in control, they speak about hidden regularity. Okay? Actually, you can take the trace if you see this as a time-space divergence equation. Then you could define the trace in h minus 1/2. This gives you more. This tells you it's in L2. Okay, so this is very important, especially for a wave structure transmission problem, where the forcing terms in my ODE are exactly the traces of the solution zeta and q of the solution in the free domain. Okay, so we need this inequality. Okay, so this is how you can handle this term. So now what happens if you want some higher order regularity. Obviously, you cannot do the same proof. The problem is that because of the boundary, we cannot apply lambda m, and even if you don't want to work with fractional derivative, you cannot apply dm neither, because dxm of u does not satisfy the boundary condition. The boundary condition, you can differentiate it tangentially, but not normally to the boundary. And dx is normal to the boundary. So this proof of regularity does not work. So what is the trick to do this? As I said, you can differentiate the equation tangentially, and the time is tangent to the boundary. So what you do is that step 1, use control time derivatives. So I do the same. I put v is equal to dtm of u, and I have that dtv plus a dx of v is equal to dtm of m minus dtm a dxu. And what is nice is that I can differentiate the boundary condition at x equal to 0, which is g differentiated m times of t, and v at t equal to 0. What is v at t equal to 0? So Shorchet, he writes dtm of u at t equal to 0. What does it mean? He means that he uses the equation as I did before to replace, so dt of u at t equal to 0 is equal to minus a dx of u plus f at t equal to 0. And so this is minus a dx of u in plus f at t equal to 0. Okay, so this actually is expressed in terms of space derivative of u in. Expressed in terms of space derivative of u. Okay, so this system, to this system, you can apply the previous, the L2 estimate. Okay, of course you have commutators to control, which are a bit different, but so this is essentially step 1. I don't have time to do all the details. And then it's nice to have time derivative, but what you want essentially is to have space derivatives. And for this, you want to use the equation and what you use is the ellipticity of the, so step 2, control space derivative in terms of time derivatives. So how do you do this? Well, you have, for instance, let dtu be controlled as by step 1, then I know that a dx of u is equal to minus dtu plus f. Okay, so I want to deduce a control on dtu from this. But this is not always possible. A has to be invertible. Okay, so I need another assumption, which is the non-characteristicity, which is that A minus as an operator from L2 to L2 is bounded by some constant M. Essentially, A has to be invertible. Okay, which is an assumption which is not necessary if you don't have a boundary. Okay, and then if this is true, then this tells me that dx of u in L2 is controlled by a constant times dtu in L2 plus f in L2. And then you have an addition to do, etc. Okay? But I just wanted to introduce the necessary assumptions to, that you have to make if you have a boundary, which is one, a Cray symmetrizer, two, the fact that the problem is not characteristic. And so let me state now the typical theorem that you have. I need to introduce some spaces. Typical hyperbolic spaces with boundary are the following. Wmt is the intersection from m equal k equal to 0 to m of Cj of 0t with value in hm minus j of r plus. Okay, so you always have m derivatives. If you have j derivative in time, you have m minus 1 in space. Okay, so it's not the same scaling as parabolic, it's the hyperbolic scaling. And we find the norm of u in this space Wmt to be the sup over t in 0t of this triple norm. Okay, with I am not responsible for this notation, which is the sum over j equal to 0 to m of dtj of u of t in h m minus j. Okay? Okay, so this because I keep here the, so it's because this is the thing is that you also control the time derivatives with this norm at time t. Okay, and then okay, and there is another one. Okay, I'm sorry. For the trace, you have the similar spaces, which is that u at x equal to 0 in m lambda t is equal to, so it's a weighted norm, exponential minus 2 lambda t prime from 0 to t. So I put a square here of dt j dx m minus j of u at x equal to 0 and t prime dt prime. Okay, and the sum over j equal to 0 to m. Okay, so you control the trace, but not only the trace, you control the trace of all the derivatives, okay, of order m, of time and space derivative of order up to m. Okay, so this being said, I can state my theorem. So the main theorem is the following. So let m be an integer. Assume that I have m compatibility conditions. Okay, so I want a solution in with m regularity. Assume that you have the Boussinesq condition. Which is mu dot e plus is different from 0 in the simple case I mentioned. In general, it's more complicated, but it's the same idea. And assume that A is non-characteristic. Then assume also that you have the norm of A in W M T cap W 1 infinity is smaller than some constant K. So I assume that my coefficients are Lipschitz. Then for all initial data in HM of R plus, for all G in HM of the time interval 0t, which can be infinite, for all F, which is in HM of 0t times R plus, there exists a unique solution in WMT to the initial bound value problem that satisfies the energy estimate, which is exponential minus lambda 2 lambda t ut in m plus this quantity here, u at x equal to 0 in m lambda t. So essentially, you have HM weighted HM norm of all the time and space derivative of u, the trace, is controlled by a function. Okay, I don't detail the constant. C times. So who do I need? I need G in HM lambda. So this is the HM norm in time. Okay, with exponential weight lambda. The difference between this norm and this norm is that here you also have the L2 norm in time of the space derivatives. G has no space derivative, so this was I have a standard Sobolev space. Plus U in HM of R plus an integral of 0 to t of exponential minus lambda t. So I have to put some square everywhere. Of probably it's f t prime and dt prime. Okay. And for lambda, which depends, of course, on this constant k. Okay? C'est fini, là? Okay, so I finish here. Sorry. So just finish here. Je vais me faire signer. Okay, and so, okay, this is it. This is the main theorem. So we have seen everything, all the tools to prove this. And so the only thing that is not proved is that if the Boussinesq condition holds, then there is a Krey symmetrizer. And so, in this case, this is an exercise of linear algebra. I will not do it, but it's really linear algebra. You can construct a Krey symmetrizer in this case, and then this is why I didn't put the assumption that there was a Krey symmetrizer. It's implied by this. Okay, and so this is it. And just a final remark. Then you have nonlinear version of this by Picker iterates. And for the application to the wave structure interaction problem, you have the trace estimates. This trace estimate allow the control of the forcing terms in the ODEs for this morning. I had this quantity as transmission condition and delta. Okay, and so you can control this term and have a well-Boussinesq theorem for the hyperbolic case with the vertical object. And this is the last one. For configuration A, okay, this is what I wanted to do, but this is much more difficult. And in particular, because it's a boundary problem, and you have to use the Lannes unknown that Thomas mentioned. So I had planned to explain it, but it was probably completely crazy to have this fitting in 45 minutes. So the idea, just because it's important, this Lannes unknowns, what is the common point with this rim boundary problem and the course on waterways by Thomas, is that there is, at some point, you have a diffeomorphism to go back to a domain with fixed boundary. And when you make the estimates, then you linearize the equation, for instance, you have to take into account the dependence on the equation on this diffeomorphism. And if it's to remove the singularities that you use this Lannes good enough. So I'm sorry, Geoffrey, and I'll let you finish.
David, lesson on Kreis theory can be applied to the equations that we are in the context of wave structure, the nonlinear shallow water. I recall that it can. Oh, okay, sorry. Okay. I recall that nonlinear shallow water can be written like that, and here it's the same, and here it's one flux, where flux is it's exactly the equation of this morning, but I just write in n-dimensional variable. It's why I add some parameter zeta. And I recall that in this toy model context, we say that it is a boundary problem. This equation omits dispersive effect, and this is why we look for the same theory for dispersive perturbation of this problem. It means that I just add here some dispersion. Of course, it's a dispersive problem if you linearize around equilibrium and look for plane waves solution. You easily see that the dispersion relation is omega square so there is dispersion. When I omit again dispersion, as someone asked, we can rewrite this problem in a conservative law form. It's still possible with dispersion, but as we will see, it's a non-local conservative law. To do it, the first step is to define the inversion operator of the dispersion operator. It means that I introduce R0 where V is the solution of the following problems. It means the inverse operator of the dispersive operator with Dirichlet boundary condition. I can also introduce, which is R1, the same operator, but with Neumann boundary condition. Neumann. This operator, you can also see that there has a regularization effect. Indeed, if I take F in Hn, then V and W are in Hn plus 2, but you need to pay a coefficient here. It's a kappa minus 2. It means that A regulation. And we will use this regulation to rewrite this equation as an ODE. I mean,
so R0 and R1 are operators acting on F, and you associate V and W.
Yes, exactly. Oh, I was the same. So, as I say, I can rewrite this equation in the conservative law. I put the variable in one variable, and I can write something like that. Where the non-local flux here is, if I omit dispersion, it is exactly but if I add the dispersion, it's now with this operator, the inversion of the dispersive operator with Neumann boundary condition. And this term can be seen as dispersive boundary layer. Of course, we call it boundary layer because if you are very close to the boundary, we have something. But if you go far from the boundary, of course, you see anything. The proof is rather elementary. For the first equation, it is the same. But for the second one, I just need to inverse this operator in this direction. It's simply if I write this problem with, for example, a non-homogeneous Dirichlet boundary condition. Oh, sorry. I go too fast. I put one boundary condition that I did something like that. The solution is simply so I just want to apply that on the first Boussinesq equation. I mean, yes. I just want to apply it with R0. So I found something like that. And what is here? It is simply here this value at x equal to 0 and the dispersive boundary layer. And to conclude, it's easy. This thing is given by the boundary condition, which is, and for this one, we can just see that I can commute with R1. This is because when you see the solution here for the derivative, you have the Neumann boundary condition. It's the end of the proof. Very elementary, but even if it's elementary, we can have a strong conclusion. For the first one, you can easily see that the problem is well posed locally in time. This is because it's easy to see that this non-local conservative law is in fact an ordinary differential equation. You look that F, there is R1, and R1 is regularization operator over 2 at degree 2, and you see one derivative, and you will see that it's enough to conclude. Okay, say, I write what I say, corollary of this theorem. I mean that it's local in time, well posed. Indeed, it's rather different than price theory, because if I take initial condition say U0 is zeta. David, you write initial or 0? I don't remember. Initial? If I look for initial conditions Hn and Hn plus 1, then there exists a unique solution which is C infinity in time for locally in time, and in space it's at the same regularity than the initial condition. The maximal time existence T is given such that there is one blow-up, and the blow-up is given by the infinity norm of zeta, q, and 1 over h, and h is 1 over zeta. Before the proof, I do some comments. First is the difference between this dispersive perturbation and the case where the hyperbolic case where kappa is null. When kappa is null, David show you that, in fact, we don't live in such a space, but we have something which is more looks like, say, the solution are here. And one question is that when you take epsilon and go, kappa, sorry, you take kappa, go to 0, can you find this type of estimate? It's a complicated question. It's because when I show you this, this theorem, I don't talk that the lifespan depends of kappa. And in fact, there's something like that. And there is also a problem that the time existence go to 0 when kappa go to 0. But I think I don't have enough time to explain how we can solve this problem. It will be probably tomorrow. And no, the proof of this theorem is also very elementary. It is because when you see this equation, this field is in fact a Lipschitz field. I say that go to Hn Indeed, it's very easy. I take U1 and U2. For the first one, it's Q1 minus Q2 Hn. So it is, you see that it is all in the good space, okay. And the second one, it's not very complicated too. It is okay. As says, this R1 is regularization of degree 2, and this one we are one loss of derivative, but the price to pay is kappa minus 2. So all the things is oh. Two and one, so, oh, where did I say? Sorry. And to conclude, it's because when I take, I don't say, but I take here initial condition. Here I will take n larger than 1, and so it's algebra. And Thomas show you that it's called Moser inequalities, that we can conclude that it is in fact when you see. In fact, here you have L infinity norm and zeta in Hn, and so the same for Q. So it's okay, and you have this coefficient, which is this one, and it's why with these techniques, the solution, the time, the lifespan depend of kappa, and we can do better and try to do something. uniform estimates with respect to kappa, but I think I will show you tomorrow. And for finding such uniform estimates, as David lesson, we need estimates of the trace of the solution U. One of the trace is given by the boundary condition, but the other one is the trace of zeta. And we will need, for uniform estimates, to have estimate of the trace. But I think I'll show you after. But now, do something with compared to the theory, it's a children's playground. I will show you how to simulate numerically the shallow water equation, the hyperbolic problem, and then how to change the numerical scheme to simulate the case of Boussinesq with a perturbation by dispersion. And you will see in that case, we will also need a control of the trace, and it's why it's another way to see that it's indispensable to have control of the trace. I need all. So remember, if I want to write something with the shallow water equation, I can write the shallow water equation in a conservative law form, where I recall that U is zeta and Q, and the flux here it's a local flux. It is simply Q and this stuff. In order to have a numerical scheme, we want a numerical scheme on what I call U and I, which is the average. Oh, before I think I will need to introduce time step and size of one mesh. We are in one dimension on air. I say that the time step is delta t, and the mesh size is delta x. And the domain of propagation, R plus, I divide it in cells, in very small cells, in the sense that it's the size of the mesh size. And since I look for a finite volume solution, here I will say that it's xi minus 1/2, and here plus half. And it means that I say it's I minus 1/2, here 1 plus 1/2, the mesh size. I say I look for a scheme on what I call UIN, which is the average on the cells taken at a time n. And I look for a scheme on these quantities. So this equation, if I integrate over one cell and divide by the size of the cell, I just find something which is exact. Here, I just need to integrate a derivative, so I take the boundary condition at x minus x 1 plus 1/2 and I minus 1/2. So up. Then I say in time, I take Euler explicit. It means that I want to change here the time derivative with Euler explicit scheme. And since it's Euler, it's the value here. It's a value at time n. Now, to conclude, I need choose a good choice of a way to approximate the flux. There are several ways. In this case, where I only consider a local conservative law, I can say that I approximate the flux. For example, I take just this one and this one. Say that approximatively and this one can be given as a function which is dependent of the value here and the value on the cell after, because you have the point here which is between two cells. I approximate this flux by one flux, which takes the value of u in this cell and u in the cell after. And if I change plus for minus, it's the same, but with the cell before. It means that it is u. There is several ways to choose j. For example, a good choice of j, it's a choice that, such that the chim will be at the end. For example, at one order chim, you can take Lax-Friedrichs. And Lax-Friedrichs means that you take j, which is simply, yes. You can take another type of chim, like Vendrop, for example, if you want a second order chim, and so on. It seems that I finish and I have a chim, but I have one problem. If I can take something which is close to the boundary, I take, I don't write the final chim, no. So final chim. Is that u it is the approximation of chim say I have one problem. If I take for E the value 1, here it seems that I have no problem here. But here, you have the first one, which is, and the second one, which has some problem. We have some trouble because in this stuff, you see that if I take this chim, I need the value at 0. And I recall that it is, sorry, say in other. This one, it is a boundary condition. And this one, I don't know. So to have a final chim, I need to give a value of this guy. In the particular case of nonlinear shallow water, the equation here with kappa equal to 0, it will be given by the introduction of Riemann invariant. It's a special case for this equation, and we will see that for dispersive case, it won't be the case. So to solve this problem, I introduce what we call Riemann invariant. Oui. Okay, it's because if I imagine I forgot for the nonlinearity, you just have a transport equation, a 1D transport equation. If I don't add this term, it's simply center chim, and for a transport equation, it's not stable anymore. So a trick of Lax is to introduce these things, which is, if you see only the advection equation, it means that it's an upwind chim. And so in general, for any flux, you can generalize, and you have at first order this guy.
dt is small compared to dx.
It's stable under CFL condition, and it means that I never remember it's delta x or delta t.
CFL for me is dt small compared to dx.
Okay, I write the good. Yes, it's good. Ah, yes, but apply here. So it's in fact this term. If you apply in this delta x, go with its delta x, and you have one delta t, which is go here, and it's like if you do advection equation, you add something here to not center the chim in time. Yes, it's a. When I say Riemann invariant, it's a very special case of nonlinear shallow water. It's because you can diagonalize this equation in this way. In this way that we can write, something like that. It's very similar to what write David with the eigenvalue. It's like something like that, where the Riemann invariant are plus minus. It's I don't remember by Hertz. Okay. It's a Q 1 plus, and here plus minus 2 over minus 1, and the eigenvalue plus minus. So what David writes, it's the same situation, and you have one which is positive and the other one which is negative. So it means that you have nice nonlinear shallow water in two kinds of transport equation. One go to the left to the right, and the other in the other side. And so we use this equation to determine the value we need. I mean that zeta n0 can be expressed as a function which depend of Q and 0, which is a boundary condition, and the Riemann invariant. I take R1 at value 0. So I just need to discretize this equation, the right to left Riemann invariant. I need to discretize to have finally find the value of this guy, and so the value of this guy. And so when I discretize these things, say up, the discretization is exactly the same way. First, you integrate over a cell. After, you need to take, for instance, explicit Euler for discretization of the time derivative. And after, you need to take a choice of the flux. And if I choose something which is very similar to Lax-Friedrich, it's a print. But when you go to the right, to the left, it means that you have n 0, oops, sorry, t minus, can take u at value n minus 1, which is already given because you know everything at value n minus 1, and at the end, sorry, it's the other side because we go to the left, to the right. And so you can, we can deduce something about this guy, and after this guy. Now, we want to generalize exactly this scheme, but in the case with a non-conservative law, which is exactly the way I write the Boussinesq equation. It means that it is 0, and here so all the steps are very the same. I just say that it's a non-local flux, and here yes, just take this thing, and I take, for instance, I take something in the center of the mesh, and here, sorry, I forgot here, of course, it's also the same. And I take something here in time, which is a boundary condition that is well known. But here there is one first difficulty, is what can I take here as a good scheme? As you see, a good choice of the numerical flux, I take something which is very local. I just local, but at the half between two cells. And here, as you see, remember, this guy is a non-local because R1 see everything. So we cannot take something like that anymore. We need to say something about the non-local way we discretize something like that. So here it's not, oh, the problem will be the same here. But here, we can proceed in two steps. The first one, you need to discretize this operator. And the discretization here is very easy. I say if I want to solve something like that, the numerical way to solve it is Wy can choose a center here. And so it's a discretized way to solve this guy. And so we can generalize, for example, the Lax-Friedrich schemes, something like that. I put a kappa. Before, you remember that it's 1/2. I add value at I plus this one, I plus 1 plus, yes, it's type, and so it's U. And here, at the end, we have exactly the same team, but you still have the problem how to find this value in the dispersive case. The Riemann invariants don't work anymore, and so we will do something. We can find an Haydn equation whose solution is exactly the trace of zeta. I come back to the theoretical part. How many times? Ah. Okay, can I just 2 minutes? Ouais, bon. Okay. Okay. So it's a suspense for the next for the next lecture. I will show you how I can find an equation on the trace of zeta, which first solves the numerical way, because I will show you that it will be an ODE, so I can solve this problem here, and I will show also how it can solve this dispersion-less limit in that case. And sorry, but I will show you in the very complicated system with mix the waves equation, which is described by this Boussinesq equation, coupled here with a boundary condition, which is linked to the dynamics of the solid. And so I finish on time. Mm.